Hello everyone. Today I'd like to talk a little bit about the x64 debugger and give a little intro into assembly. So, what is it? It is basically a binary debugger, and what it does is it will take any piece of executable or a Windows DLL file and it will break into its assembly instructions. It is very useful for reverse engineering because no matter what it does, you can't hide code there. You can't hide from the binary. That's exactly the instructions that will be executed by your CPU. And when it comes to advanced dynamic malware analysis, it is obviously not the first tool you should use. You will follow your procedures. You will start with the static analysis, for example, study your strings, and then you maybe you try to execute that malware, see what it does, and check the behavior analysis. It is very useful for situations where you have polymorphic code, for example, or a highly obfuscated code. One of the methods of obfuscating code, for example, is by using packers. Packers are technology that were developed to hide intellectual property from the debuggers. However, obviously, hackers started to use it to hide their malwares from analysts to prevent them from understanding the malware's behavior. So, Packer basically is a set of compressions and encryption that will change the way the code is executed. There are some commercial tools like UPX and Themida, and if that's the case, if you can't identify those packers, you can just use an automated tool to unpack it. However, some smarter hackers they will use custom packers, and if that's the case, you most likely need to use some tool like a binary debugger. New Fox mentioned here that the difficulty with using x64 debugger is obviously knowing assembly code. But once you get there, you can just pick apart malware samples like a surgeon with a scalpel. Okay, so let's take a look how it actually looks like. If you're running a Flare VM, you have it available here instead of debuggers. Um, or you can just simply download it from GitHub. Just a quick Google for x64dbg and you can quickly find it. So let's try the Windows calculator. So let's open it here. Okay, so as we can see, it's executing. I will run it and the calculator is running. So this is the code needed for this is the code that's actually executed when you run your calculator, and it looks quite complicated. So let's take a look on some basics of assembly first. It is not in the scope of this video to fully teach anyone assembly, but we should start with some basic concepts. For example, most of computers we have nowadays are based on the von Neumann architecture, basically a way of which separates the memory into main memory, which is usually RAM, secondary memory, which is it could be like a hard disk, and the CPU. Inside of the CPU, we have the ALU register and the control unit. So ALU is the arithmetic logic unit. I came from an electronics background, so I learned about logic gates before actually learning programming. So if it's not familiar to you, it's not important. I'm just showing it to illustrate. If you are familiar with digital electronics, it may makes it easier to you to understand what an ALU does. So it basically takes two inputs here and it will give you a result in this other terminal here. And what determines what kind of operation is going to happen here is the opcode. So we can be introduced to this concept of opcode. Understanding a little bit of what the ALU does, you can understand a little bit more of how assembly works. The next important topic are registers. There are many types of registers, but here are some of the main important ones. Notice that there are 64-bit registers and 32-bit registers. They are named basically the same except by the fact that they start by R in case of 64 bits or E in case of 32 bits. These registers are used in many different situations depending on the function. For example, they could be used to transfer values to the memory, similarly to the parameters of a function. Also, we have these very important pointer registers because they will provide information about the memory, where the memory is pointing to. The most important perhaps is the EIP, which is the instruction pointer that will be pointing to the next instruction in memory. In regards to the memory, what's important to know is that there are 5 separate regions in the memory: the code or .text, the .data, .pss, also heap and stack. Stack is maybe one of the most interesting for now. It's important to notice that the stack grows from the top addresses downwards to lower addresses, and some commands involving memory are move, push, which puts data into the stack, or pop, which removes values from the stack. So the instruction set architecture is a set of commands that are interpreted by the CPU. An example of an add instruction. So this add command here, this instruction is represented by a binary number. Those variables here could be a CPU register, for example, or we could see here memory addresses as well. If we look back to this picture here of the ALU, we can see that the opcode is nothing but terminals connected to logic gates, and that's how the CPU is built internally as well. The instruction set is provided by the vendor into a document called datasheet. Think about the nightmare it would be for the developers if each model, or at least each vendor, had its own one instruction set. So what happens is that, for example, Intel and AMD, they partner up and they have a standard instruction set that they use, so you can compile your code without having to inform much other than if it's a 32 or 64 bits processor. Just to mention, there are also CISC and RISC architectures, but because we are investigating a Windows 2, so we're focusing on CISC instructions. Now let's go back to x64 debugger and let's try to understand what are all those information here. So we have at least 6 important areas. Um, this is the main area, the CPU disassembly codes. So here are our instructions. In this first column here, we'll see the memory address and what instruction is located there. So here are the actual opcode, and here is the mnemonics to what this opcode is doing. In this other area here, we can see registers information. So we can see the EIP in the EAX, EBX, ECX, all those main important registers. We have the stack information, so we can see it grow and shrink as pops and pushes are run. This little window here also shows the stack trace. Another important or interesting area is the dump. Depending on the situation, it's where you're going to look for information that's stored in the memory. Some other interesting features are, for example, breakpoints, where you can see all breakpoints listed. We'll see a little bit more of breakpoints and their importance down the road. Memory map, that will show data stored in memory and the addresses where the data is stored. So as we mentioned before, you have the .text.data, for example, and you can see where in memory it's located and its size. The call stack can be interesting to track DLLs or specific functions being called. You can use commands as well. For example, you can create a graph. This functionality is similar to what IDA does. And another very interesting feature are the plugins. You can install public plugins, or you can script and develop your own tools to analyze code as you wish. Okay, so let's restart this code. Let's run it. We have our calculator. And let's try to understand how code is controlled by these buttons here. The easiest way to control the execution flow is using the F keys. We can click here in the bug and you can see a write down of each key does. So those main important ones are run F9. This is similar to running the code as if you were just using the software. 7, stepping 2 is used when you have, for example, a function call. If you use F7, your code will be sent to that function call. There's the step over that, for example, will instead of jump, it will just follow the next instruction in the memory. Okay, now, so before trying to analyze something more complex, let's look into something very simple as a hello world. So here we can check on this hello world code and we can run it. It just prints hello world. Okay, so let's go back. Let's load our hello world program. Something that's worth mentioning, I deactivated the system breakpoint And what it does is when you load a software, it will load all the DLLs, and then it will put a breakpoint where it starts. So if we don't activate it, we'll have to run into the actual program starts. So I just deactivate it. So when we load our program, it starts exactly where the program instructions start. So we can have a quick demo. Um, I'm using here another tool called Cutter. I loaded that Hello World program here, and we can use it to identify exactly in which memory address the main function starts. And we can copy that address. We can come back here, use Control G, paste the address, and go right there. So here is exactly where my main function starts. And followed by that, we can see the call for the printf function. What I'm doing here is I'm setting breakpoints. So my EIP currently is in this address. Let's click there. I moved the software execution to that memory address, and I'm pressing F9. So what should happen now is it maybe will find some other system breakpoints, but at some point it will stop right in our, here it is, it stopped right in our main function. So we can see what's happening here. Let's open the terminal. That's the hello world here running. Now I'm pressing F8 to step into the function. So here we should see now the next instruction should be the call of this printf function. Here it is. It prints our hello world message. Okay, so what else can we do with it? So because we have access to basically all the memory addresses, we can manipulate basically anything. We could, for example, try to manipulate this hello world message in the memory. So let's start it. We can see it just restarted here now. Let's press F9 again to get into right before it calls the printf memory. And as we can see, the instruction right before this one moved the hello world message to this memory address here. We can follow this memory address. I'm going to follow in dump and hello world. So here it is. We can find our message here, and we can come here, binary edit. We can try to change it. We just need to keep the same amount of characters. Okay, now let's press F8 to get into that function. And there it goes. So we took that compiled program and we manipulated its memory to output whatever we want. This is very interesting for when, for example, when analyzing a malware, you can just change flow of the execution. You could, for example, avoid it from being executed, but still execute some parts you'd like to study.